Diffusion is basically very important conceptually for anesthesia because that's how actually we move gas in and out. When we're talking about from physiology, we're talking about diffusion of two gases most of the time, which is oxygen and CO2. It's basically the transfer of gas from the alveolar volume into the blood. It is a passive event, so it consequently follows the laws of diffusion, which is surface area, molecular size, how much diffusion, how much area you have, plus how much thickness you have. Basically, all gases that enter your lung basically follow this mechanism. If you have a high concentration of one gas in one compartment, it's going to try to equilibrate with the other compartment, which is simple. That's it. Fick's law describes how gas travels through the membrane, so the rate of diffusion of gas through a tissue slice is proportional to the surface area. In other words, so it's directly proportional to the partial pressure difference in the solubility of the gas in the tissue. CO2 is actually 20 times more soluble than O2, so usually diffusion is not going to be a limitation on CO2. On the other hand, what's inversely proportional is the thickness of the membrane and the square root of the molecular weight. So what you end up with is this equation. You can memorize it if you want to. Instead, I get the concept straight in my mind. If molecular weight goes up, what should happen? It should decrease. That makes sense. If thickness goes up, it should not be able to get across. That's right. So just keep the concept in your mind instead of memorizing the equation. Again, this is a nice little drawing showing you what happens with diffusion. You have so many particles on one side and you have no particles on the opposite side. Eventually what's going to happen is this is going to equilibrate or try to equilibrate depending on the diffusion capacity of that molecule. Lung is basically not a static environment. It requires two concepts, very importantly. It requires adequate ventilation and also adequate perfusion. And different gases act differently because blood has two components. It has plasma and red blood cells with hemoglobin in it. Okay, so it has a special protein that acts as a carrier. Oxygen, when it diffuses across, will bind to a certain degree in plasma, but it's very, very low. Okay? Instead, most of the oxygen is carried in your hemoglobin. So hemoglobin acts as a massive sink that begins to pull the gas across much more rapidly than it would otherwise be possible. If you were to just put plasma next to an alveoli, the amount of diffusion capacity of the oxygen would become very, very limited quickly. Okay? But because the hemoglobin acts like a sink, it sucks it right out of the cytoplasm, or in this case the plasma, and it causes a gradient to still come across. It helps pull the oxygen across as a consequence. What actually has a higher affinity to hemoglobin than oxygen is carbon monoxide. And as a consequence, it doesn't take much to get in your alveoli before you get in trouble. Because now, once you start filling up the tanks, the actual trucks with carbon monoxide, then you start killing your oxygen gradient. Okay, so you get, even though you're delivering oxygen to that individual, it won't come across like it should. So how different gases interact with our blood and the alveoli is this example. What you're looking at here is time on the bottom, and this is blood flow going through the lung over time. Okay? If you look at carbon monoxide, it's almost linear. So it basically doesn't really care. It's so rapidly uptaken that it doesn't really care about hemoglobin at all, okay? Or time at all. If you look at the other two gases, which is oxygen and nitrous oxide uptake goes from 0 to 100, whatever the value is. In this case, we're giving 100 nitrous. That'd be pretty much hypoxic. That individual will uptake this nitrous oxide up very, very fast. Okay, so nitrous oxide, where's it going? It's not going into the actual hemoglobin at all. It's going all into the plasma. Okay, so nitrous oxide, even though we're giving it in high values, doesn't really destroy the hemoglobin carrying capacity. Okay, but it does affect the plasma concentration of oxygen. So that can become a problem kind of pretty quickly. If you look at the partial pressures of an oxygen under normal conditions, let's say 100 is what your alveoli are seeing, it only takes a normal individual to basically reach maximal upload around 0.25 seconds. The other 0.5 seconds, which is the total 0.5 seconds, is reserve. So most people, when we're running and going at full bore, when our velocity of blood increases, so our actual time in capillary goes down to around 0.25, we're still getting plenty of oxygen and we're happy. No problems. But if you have a problem with diffusion capacity of any kind, what ends up happening is that under rest, you're okay. You're still reaching full capacity at 0.75 seconds. But if you were to run or start moving around and your blood flow increases in your lung, and now you're down to 0.25, now your partial pressures of oxygen drop down to around 60. What's your saturation going to fall at that point? Come on, 60, 90, 90%. Remember, PO2 of 60 means the saturation is going to be 90%. So this individual is going to go from a saturation of 100% with exercise is going to go down to 90%. Pretty quickly. That's at room air. Okay? Does that make sense, or did I lose somebody? I lost you, didn't I? Okay. All right, let me back up. Oops, sorry. This is partial pressures, okay, which in essence is what we call the PaO2. Okay, that's the arterial O2 that person has, which is the dissolved oxygen. Okay, when we talk about oxygen dissociation curve, and when we talk about this guy here. Okay, the crossover point, 90%, the PO2 is 60. That's a 60-90. So if that person is basically at 2.25 seconds and you come across and that value is, let's say, 60 there, then that person's saturation is going to be 90%. Make sense now? Okay. So what I'm trying to show you is that if people have abnormal diffusion capacity, at rest they're doing okay. But as soon as you make them walk or move around, they begin to desaturate. And as a consequence, they will develop dyspnea. They will become symptomatic very quickly. Okay? Now, the way we describe this interaction is we either describe it as diffusion limited or perfusion limited. Okay? Diffusion limited basically has to do with carbon monoxide. Okay? Carbon monoxide is so rapidly removed by the hemoglobin that there's no equilibration with the alveoli, and they basically degrade the uptake.
Okay. If you look at the other one, which is perfusion limited, which is nitrous oxide, there's no combination with hemoglobin. In other words, you're going directly into the plasma. So what's important for that is how much uptake is going to be up to blood and alveolar concentration rapidly equilibrate. So when you're looking at oxygen is normally perfusion limited, just like nitrous oxide. Because you look at the curves, nitrous oxide and oxygen are very similar in curves. They're on top of each other. So they're going to be more perfusion limited, which means that, here's what I'm trying to tell you. If I slow down my perfusion to the lung, what's going to happen to my uptake of nitrous oxide? It's going to go down. And also my uptake of oxygen is also going to go down. But even if I change my perfusion with carbon monoxide, it doesn't really matter. The uptake is so fast that it doesn't care. Okay, so it's not perfusion limited, it's diffusion. Diffusion is limitation with that. So if I change my diffusion, carbon monoxide will become less. It's a way of picking up if you have a diffusion problem. So one of the tests that we can check on to see if membrane thickness is getting bigger, okay, let's say somebody is developing ARDS, is we expose them to low levels of carbon monoxide and then we draw blood gas. If the CO levels, carbon monoxide levels, are going down, that shows you that I have a diffusion limitation. Okay? Now, basically the way you look at it is think about it as a sheep. This is the best analogy that I can think of. Maybe it's not the best in the sense of thinking about it, but imagine that you're in a giant field. In this giant field you have sheep. Okay? And you have, let's say, 100 sheep. And I'm going to tell you that I'm going to have no gates, and I'm going to call the sheep on the other side because I'm going to have lots of meal for them. So they're going to rush across the field. So the only thing that's limiting them is nothing, except how fast their little feet will make them move. Okay? And that will be, we'll call that how well they can diffuse across that field. The other way of looking at it is taking the other concept, which is a perfusion limited, and now instead of having an open field, now you put a gate in. And you only put in a gate that's big enough to let 10 of them go through at one time. Okay? So in that situation, it becomes time dependent. Carbon monoxide, if you look at it right here, it's totally time independent. The degree of uptake that you get is almost no difference between 0.25 and 0.75 seconds. It doesn't really matter. The sheep are going to get across all in 0.25 seconds. Okay? Versus if you put a gate in place and you limit it, okay, the number of animals that can get across per time becomes limited. Okay, that's why we call it perfusion limited. Okay, the way you think about the gate is, think about it as how much perfusion I'm getting there per second. So in other words, if I make my gate smaller, which means I'm making perfusion drop, what happens to my ability to get the sheep across the field? The answer is it becomes limited, it becomes less. Okay. Now, if you look at oxygen, that's one concept. Okay, the next concept is oxygen transfer to the blood. Okay, so you have to get from the atmosphere, it has to get all the way down to your lungs. So, in what you're looking at atmospheric conditions, that's your FiO2. And FiO2 in the atmosphere that we live in is around 21% oxygen. Okay, if I was to go up to Mount Everest, is my oxygen FiO2 any different? No, it's still 21%. Then you go like, geez, Dr. Nolan, that means why does a person die when you go up to the top of Mount Everest? The oxygen levels are still at 21%. It has to be to do with 21% of the atmospheric pressure. As you go up in altitude, what happens to atmospheric pressure? It drops. Okay? I had a friend of mine who went to the Dead Sea. Okay? And I asked him, I said, what did it feel like? And he looked at me kind of funny. He says, what do you mean? Did it feel funny? And he says, yeah, but I've never had anybody ask me that question. And I said, did the air feel heavy to you? And he said, yeah, it actually did. It felt kind of strange. It felt like I was breathing through water. The Dead Sea is one of the lowest places on Earth. Okay, so when you go there, the atmospheric pressure is higher than normal. It's like 890 or something like that. So the air actually feels heavier on you. Okay, it feels weird. So what happens to FiO2? What happens to oxygen capacity at that? Does it improve? Yeah, absolutely. Okay, so what happens at rust in the Dead Sea? Does it go up or down? It increases dramatically. You want to see a car disintegrate to dust? Put it at the bottom of the Dead Sea. Okay, so different degrees of percentage of oxygen can definitely be caustic. Now, all right, so if FiO2 is a fraction of your atmospheric pressure, if I tell you that FiO2 is at 1, that means you're at a 100% oxygen delivery. I mean, 100% of the oxygen of that pressure is going to be 100 molecules in that. I mean, 100 boxes in that, okay? 100% of the boxes. So if you have 760 millimeters of mercury, and I tell you that your FiO2 is a 1, that means 760 of those boxes are going to be filled with oxygen. Okay? Normal value for FiO2 is 0.21. Some books will say 21%, which makes a confusion for students. Okay? But FiO2 is basically, should be used, the highest value you should denote is 1, which is 100%. Now, once the gas enters into your lungs, enters into your mouth, it immediately encounters another molecule. That first molecule it encounters is not CO2, but it's actually water vapor. Okay? So when you have to do these equations, you have to consider always that water vapor is getting in your way. So when you're let's say we're at sea level. That's 760 millimeters of mercury. Okay? As soon as you breathe into your mouth, 47 boxes are going to be uptaken by water vapor. So right away, that's going to eliminate your capacity to carry oxygen into your lungs. So that's going to give you the value of 713. 713 times 21%, or 0.21, is going to give you a magical value. This is amazing in mathematics. It's so simple. It gives you a number of 150. Just think about that. What the hell's the chance of it, excuse my language, what's the chance of it getting down to a simple mathematical formula where you get a magical number of 150? Okay? So that's 150 boxes that you have available of oxygen in your mouth. All right? So now it moves from there to the alveoli. Once it gets into the alveoli, you have one more gas that's going to consume boxes, and that's going to be CO2. And the CO2 ratio is what we call the R value, which is underneath it. The R value is at 0.8. So if you're breathing at CO2 of 40 in your alveoli, the R value being 0.8, which is underneath the number, gives you this magical number again of 50. So 150 minus 50 is 100. So your alveolar PaO2 at sea level at 21% oxygen is at 100. And then that's your gradient. That's what's inside your alveoli. That's what we call the alveolar gas equation. That's what's going to push into your bloodstream. Okay? So if my gradient diminishes, which means if I go up in altitude, what happens to my PaO2? It drops. So then my gradient becomes less. And if my gradient becomes less, there's less energy to push into to get diffusion to take place, and less is going to get into my into my blood. I'm going to show you a picture of that in a minute. So eventually the oxygen gets through the alveoli and it then binds to the hemoglobin, which is really more important than dissolved in the plasma. This is the alveolar gas equation. This is what I just told you about. This is a memorized, if you want to memorize it. Some people have to memorize equations, and said, I don't memorize equations. I just think it through. That's why I just talk to you about the whole equation without thinking about it, without giving you the equation. Instead, I'd rather give you the thought process so you, at 2 o'clock in the morning when you're tired, you can figure out the equation without having to look it up. Okay? So here's how it works. P atmospheric, in this case, was 760. Water vapor pressure is 47. Okay, so that's 713. Times 0.21, which is FiO2, in this case at room air. So we're down to 150. Minus the PaCO2, which is 40, which is the arterial CO2 over R, which is 0.8 in this case, which is going to give you a total number of 50. So you're going to get the big AO2 is going to be 100. That's at sea level, and at FiO2 is at 21%. Okay? Now, if anybody ever gives you a test question where they don't give you the atmospheric pressure, water vapor pressure, sometimes they won't give you the water vapor pressure, they'll tell you that water vapor pressure is normal, which is in that case 47. But if they don't give you the atmospheric pressure and they don't give you the FiO2, and then they tell you, it says, figure out the A gradient. The answer to it is insufficient information to figure out what the answer is going to be. Okay, sorry, but they did that to me, and I just was fuming mad when I figured out what they were trying to do. I actually missed the question. That's why I still remember it to this day. Okay, but you know, I thought it was a trick question, so I ended up not thinking it through. What they wanted you to do was just to develop the alveolar gas equation and then convert that and be able to do the A gradient. Okay. Now, normally transfer of oxygen is fairly rapid, okay, but transfer of CO2 is even more rapid. So what they're trying to show you here is this alveolar gas equation is pretty important in the sense of oxygenation issues. Okay, and I sort of walked through this already, so I'm going to keep going. This is all the actual equations of mathematics which I already described to you. And going through the whole thing, keep going down. This is all dead space, okay? That's why you're not, that's the gases are affected by the CO2 coming out, which is 50. So that gives you the alveolar O2 down here at 100. And that's the gradient that's now establishing the oxygen from the alveoli into the capillaries. Now this is another way of looking at it. This gives you the environmental pressures out here, okay? And then when you go into your mouth, you go down to 150. This is the. Then you go down to the alveoli, you're down to 100 because of the CO2 coming out. And then you're going to the next step, which is conversion of alveoli to the pulmonary artery, into the capillaries. Okay? The pulmonary artery is staying up here, and then this is all pretty much at the cellular level. So this big fall from here down to here is at the cellular level. This is when the capillary exchange is taking place. And so that's when you dump a lot of oxygen. When you come back, your PaO2, of course, is fairly low, so your venous O2 is around maybe 60. Okay? And that's if you're under general anesthesia. If you're looking at somebody who is more, normal, you're looking at most like PaO2s around 50 on the venous side of it, which is going to give you a saturation around 70%, which is what we usually see on SpO2, 70%. Now, one of the limitations of diffusion is, of course, atmospheric pressure. So when you go up in altitude, what happens to atmospheric pressure is it continues to fall. If you look at a normal individual at sea level, the maximum PaO2 that you can really achieve is 150, but when you start taking away the CO2 and everything, you're down to 100. When you're moving up into the mountains, then your actual atmospheric pressure dramatically falls. If you're up in the Andes, you can drop down as much in the 76 range. If you're up to Mount Everest, you're basically, when you're hitting the peak, you're looking at 43 at your alveolar level. So that's pretty low. Okay? Now, the only way you can actually survive this at 43 is, think about it. What's the other gas that's coming out? CO2. If CO2 is coming out at 50, then this value would basically mean that the oxygen levels would be 0. So you'd be dead. And that's what actually would happen to you. If you parachuted into Mount Everest and you did not acclimate, you would be hypoxic and dead in a few minutes. But the reason that these guys can climb to this altitude is that they hyperventilate themselves to such an extreme that their CO2 level in their blood is at 0 or 2. That's really, really low. So that means when it comes out against this gas, it's at 41, 43 is what that person's gradient is going to be. That's still not sufficient to survive in for long term, but these people's sats are running at between 70 to 80. Imagine how bad that would feel. One of my friends used to volunteer and go up to the base of Everest to help in a clinic. And he said, we weren't worried. Most people, even myself when I was there, he told me, he says, I would live at around saturation 85%. I'm going, what? That's your baseline? He said, yep. So your hemoglobin levels went skyrocketing upwards. Most people's hemoglobins at high altitudes are around 16, 17. Okay? So they have a hyperviscosity, as you can imagine. But what ends up happening is you get more carrying capacity and you tolerate it better. But he said we got worried when they got down to 65. That's when it was serious and you needed to get them off the mountain pretty quick. Okay? So it's amazing. That to me would be, I'd be freaking out in the operating room. Okay, so what does this mean is that this gradient that you establish here, this is an individual at sea level with a PaO2 at FiO2 of 21%, and they'll actually get the alveolar oxygen level will be around 100, so that would be the maximum gradient. And under normal conditions, you get that gradient is more than enough to uptake all the gas, so that person is very happy and well saturated at that point. If you, in other words, make this person exercise, you will see that that person's PO2 will fall dramatically, and that person will become symptomatic. They will start desaturating as a consequence. Now this same drawing, let's look at it, what happens if you go up in altitude. And, I didn't show it, but there's another graph in the book that shows you this. It's a little bit confusing for students, is they'll see it on LBB, okay, and the gradient now goes from this, because they go up to high altitude, the PO2 will actually be only 50. Okay, when that happens, of course, now this person will become symptomatic even at rest, okay, because it'll take, the gradient is less. And hopefully I'll show you the picture here in a little bit. What you're seeing in diffusion is that you want to get gases in and out. Diffusion is usually very efficient for CO2 removal, versus oxygen is a little bit less so 20 times less than CO2 diffusion. But eventually most oxygen gets across adequately, and the reason it's able to do that adequately is because the hemoglobin begins to suck up the actual oxygen that's dissolved in the plasma. And it actually helps maintain the diffusion gradient going across. If you don't have enough hemoglobin, yes, your PaO2 seems to be okay, but your uptake of oxygen diminishes rapidly and becomes a limitation. So diffusion of oxygen across the blood gas barrier at rest, the PaO2 in the blood virtually reaches that of alveolar gas after about 1/3 of its time, which is around 0.25 seconds. Blood spends only 3/4 of a second in the capillary at rest. So on exercise, the time is reduced to about 1/4 of a second, and that's where it becomes a problem. So the diffusion process is challenged by exercise, alveolar hypoxia, then thickening of the blood gas barrier, which then becomes a diffusion capacity issue. This is with a picture I was wanting to show you before. Okay, this is the example where you see in the book of low PaO2. Okay, this is an individual that has altitude, okay, for example, or is not breathing enough to get the alveoli adequately oxygenated. Either one, you can see that at rest, okay, even people that are normal, if you're at rest, are okay, but if you start exercising them at all, they become rapidly symptomatic. Their saturations begin to fall, and that individual becomes very grossly symptomatic. If you were to look at the actual value of saturation, this person would be a PaO2 of 50. Okay, so you're looking at saturation maybe around 85%. So that person would be already symptomatic. But you make him exercise just a little bit, you'll push him right off the edge. You'll almost be at P25, 27, which is the P50 value. So you'll be at 50% saturation pretty quickly. The abnormal patient, of course, is now desaturating very, very aggressively early on. Even with a little bit of exercise, they're going to fall apart even more rapidly on you. And this is again an altitude picture showing you what happens with different PaO2 values. This is not for the test. Somebody was kind of nitpicky a few years ago and told me, so you don't know the altitude of these things, and then going like, you're right. So I pulled up this thing and put it on there. So anybody who's really a mountaineer, they can look at this more carefully and have fun at it. And it's kind of interesting. The measuring of diffusion capacity can be done by carbon monoxide because the uptake of this gas is diffusion limited only. The normal diffusion capacity is around 25 milliliters per minute per millimeters of mercury. And if you look at diffusion capacity, it normally increases with exercise. The reaction rates with hemoglobin, which is the uptake of oxygen, diffusion of oxygen to the plasma, to the blood gas barrier, it's got to go through plasma first and eventually the red cell wall interior. The reaction of O2 with hemoglobin is fast, but because so little time is available for capillary, this rate can actually become a limiting factor. Resistance to the uptake of oxygen is attributable to reaction rates, probably about the same as that due to diffusion across the blood gas barrier. So you're looking at about 50-50 combination. And then the reaction rate of carbon monoxide can be altered by changing the alveolar PaO2. And in this way, you can separate the contributions of diffusion properties of blood gas barrier and the volume of the actual capillary blood can be derived. That's a very more complicated equation, which is just kind of nice sometimes when you have an issue which one is causing problems of diffusion capacity or is there something wrong with this red cell membrane wall, which is sometimes important. The interpretations of diffusion capacity in carbon monoxide is normally limited by area, thickness, and volume of blood in the pulmonary capillaries. In disease, you can see distribution of diffusion principles, alveolar volume, and capillary blood can also affect diffusion capacity. If you look at carbon dioxide transfer across the pulmonary capillary, it is so fast that usually it's not an issue with solubility or diffusion capacity. So CO2 transfer rates 20 times faster than O2.